um, similar, but here's the deal. It goes a little something like this. The minute you see that geometric idea, you think, oh, it's even your nose. It is kind of like that, but a little different. So check this out. You have lots of functions. Sometimes you put a number in and you square root. And when you square root a number, what do? You say what times itself equals that number, right? And there are other functions. Sometimes you take a square, in which case you take the number and square it and spit out a number. Sometimes you take the log of a number you put in and you get all sorts of results. Now, in calculus, sometimes you have a function that's defined as an integral. Now that integral is in action. It's like taking the square root or a log. An integral is a function. So this is what you would call as an integral defined function. And you should understand it on two levels. One is as the antiderivative of whatever the function is. Okay? You should also understand it on a little deeper level, and that is as an area accumulation function. G is an area accumulation function, and it goes a little something like this. Now let's start with the variables here. You can see right away that it's got a little funkiness with the variables. It feels like g of x should be a function of x. And yet over here, there's some u stuff going on. You follow? Now, if you were to look at this then, it's g is a function of x because if I use the fundamental theorem to do a definite integral, what's the first thing I would do? You find the antiderivative. Now let's say it's pretty common in calculus that you let capital F equal the antiderivative. Wouldn't this be capital F at x minus capital F at -3? So in the end, when I took the antiderivative and put in x in place of u, the end result would be a function of x, not u. All right? Now consider this though in a little different way here. If I were to look at what g does, let's look at a few values. If g is defined this way, and I call this the graph of f. Now, let's start here. U actually is the things that are going into f. F is a function of u. So u is kind of like the x values. Are you with me? Or the input values. You follow? Where the x is on this, that's kind of funky. I'll show you. G of -3. If I look at what's g of -3, well, go back to this, what g is defined as. G of -3 would be defined as the integral from -3 to -3 of f, which is basically the area under f from -3 to -3, which is 0. Of course, there is no area there because it didn't go anywhere. The width of that region is nothing. You follow? So if I were to sketch G, which you typically don't do, but just for the fun of it, when x is -3, G would be nothing. Okay? All right. G of -2. Now that's -3 to -2 in the integral. If I were to show that visually, it would be something like this. This much area. The area you accumulate in going from -3 over to -2. So G goes back, I'll go back to this. G is an area accumulation function. Now if I were to do this well, up here maybe, if I were to try and quantify that area, it's a little more than one box, maybe 1.5 boxes of area, so maybe 1.5 units. You with me? Just taking a rough estimate. So I might say that by the time I went to -2, I had accumulated about 1.5 units of area. Again, estimate, just ballpark. Cool? You with me? Now again, remember this G value then represents how much area is accumulated. by the time I go to that x value. G at -1, so that's area accumulated there. Area accumulated is about 1.5 square units. G at -1 would, again, be the integral from -3 now to -1 is where that -1 goes. Graphically, that would be the area going from -3 a little further up to -1. And I think you'll agree that you just gained more area. So G just increased. If I were to try and quantify that, it might be more like maybe 1, 2, 3, ballpark 4, a little more square boxes. Yeah? Are you with me? Okay? So let's go on here. Something like that. Again, this is ballpark estimate. You're not going to be asked to actually graph G. I'm just conceptually speaking. You with me? G of 0. G of 0 is the area under the curve from -3 to 0. Well, that's the whole quarter circle. Do you agree? What's the area of the quarter circle? 1/4 pi r squared, or 9 pi over 4-ish. So what's that? About 27 over 4, 28 over 4, about 7 units. Right? Okay? So it's going to continue to grow. Man, I wish I would have scaled this better. 7. Now, in terms of how fast it's growing, it's actually growing faster and faster, because when I went 1 unit over here, I gained a little bit of area. But when I went another unit here, I gained more area. So the rate at which I'm gaining area is getting bigger. And this, now I'm really gaining area faster, because that is so much area in that last stage, right? If you go G at 1, G at 1 sounds good. G at 1, -3 to -1 to 1, excuse me, of F. Now we're starting to accumulate area in the triangle. Is that positive area or negative area? Positive. So will my G get even bigger? It will. But in terms of how fast I'm gaining area, this 1 unit wide region is not quite as much area there. So I'm still gaining area, but I'm not gaining it as quickly. Cool? When I hit 1.5, I'm going to get the whole triangle area. 1.5. So I could actually calculate that. 1/4 of pi r squared plus the triangle is base times height divided by 2. So I'm feeling something like 9 pi over 4 plus 1.5 times 3 over 2. That's really gross. But, that's ballpark of what, 4 point, that's about 2-ish, 2.25-ish. So altogether then I go up a little more, 2 units more, but again at a decreasing rate. You follow? Are you with me? Okay. But happens when I go to 3. What about that area? Well, that's -y, so I'll get negative area. This is signed area. So G at 3 is going to be a decrease from where I left off, because when you go into negative territory, you're picking up negative area. And so after 1.5, you're going to start to see the area decrease. Where will it end up equivalent to? Think about the way those two areas relate in those triangles. This negative area is equivalent to that positive area. So G at 3 will be the same as G at 0. Okay? Are you with me? All right. You could therefore think of G as an area accumulation function. Now let's talk more common way to do these kinds of problems here. You don't typically graph like that. I just do that once I'm teaching, just so you can see that G is about gaining area as you go. More to the point in what you'll see on the AP test and in calculus questions be this. If you understand this on 3 levels, then G is the antiderivative of F. Now notice the X and the U can be left out. Don't worry about those, all right? Now, hi, you're here. Let's go a derivative level. What if I take the derivative of both sides? Then the left side is G prime. What's the right side? So the right side is the derivative of the antiderivative, which is just F. So G prime is equal to F. Take the derivative again. The left side, the derivative of G prime would be G double prime. And then the derivative of the right side is F prime. All right, now those are going to govern a lot of the questions, so we'll come back to that in a second. Now, if you combine those big ideas with some huge ideas that we've done forever, for example, when a derivative is increasing, the function, when the derivative is positive, the function is increasing, or fun is increasing. When the derivative is negative, the function is decreasing. When the derivative goes positive to negative, the function has a what? If the derivative goes positive to negative, the function has a max. If the derivative goes negative to positive, the function has a min. All these are big ideas of calculus that you should know. To do a tangent line, you need a point and a slope, and the slope comes from the derivative. That's a big idea of calculus. Let's talk second derivative, where the second derivative is positive, the function is concave up. Where the second, I'm running out of room, so I'm going to ignore the negative. Second derivative changes signs. What happens if the second derivative changes signs? It's an inflection. Okay, now, all these ideas plus those together make a very common question. Exercises in calculus here. So, imagine this. It says, now remember, this is the graph of F. You're talking about, but all these questions are about G. So please don't just look at the graph to answer these questions. You have to make an inference. All these require an inference that needs to be stated. So let's go here. Find where G is increasing. Big idea of calculus. G is increasing if G prime is positive. G prime, now we connect it to F because that's what we're getting. G prime is equivalent to F. So to answer the question, G is increasing where F is positive. So F is positive on what? -3 to 1.5. Okay. So you're going to start with the big idea of calculus. Where's G increasing? When the derivative is positive. Then you connect it to the function here. That's where these ideas come in. G prime is equal to F. And then you say, all right, well, if G prime needs to be positive and G prime is F, then F is positive on blah. Let's try this one. G is concave up. G is concave up if, what happens? Big idea of calculus. If G double is positive, and let's combine those two steps into one. And what is G double's relationship to F? F prime, and what is F prime's relationship to F? F prime represents the, the derivative of F, but what does graphically F prime represent for the graph of F? slope. There you go. Okay? This actually has got two levels of connections. G is concave up if G double, which equals F prime, which equals slope of F, is positive. This is on blank. Well, all right, so G double needs to be positive. G double is the same as F prime. F prime is the slope of F. I need to find where the slope of F is positive. Where's the slope of F positive? -3 to 0. Are you with me? All right. Find where G has relative extrema. Categorize them as mins or maxes and justify. So, big idea of calculus. G has relative extrema. Let's go with max. G has a max if. Did you hear that? Oh, okay. I must be going crazy. G has a max if what? What's the big idea of calculus? Max if G prime changes positive to negative. Now we're going to, in addition to saying that, we're going to make the F connection. G prime, which equals F, goes positive to negative. And does the F graph ever go positive to negative? Now you're talking the F values, or the graph itself, going positive to negative. So does that happen? Yeah, right there. This happens at x equal 1.5. Okay? Would you agree that G has a min if G prime, which equals F, goes negative to positive? Does that ever happen where the graph goes negative values to positive, going from below the axis to above? Does that ever happen? No. Okay? Typically, you wouldn't say something that doesn't happen, but just for the note's sake. All right, find the equation of a tangent line to G at x equals 0. So, what do you need to run a tangent line? You need a point. A point. X equals 0, G at 0. What's G at 0? Okay, go back to the definition of G. G is defined as the area under the curve from -3 to, in this case, 0. And that is 9 pi over 4. That's the area in the quarter circle, 9 pi over 4. So the point we're working with is this weird 0, 9 pi over 4. Cool? The slope. The slope is G prime connected to F. G prime is equivalent to F at 0. What is F at 0? What? 3. Yeah, it's the y value at 0, which is 3. So what's my equation, my tangent line then? Y minus 9 pi over 4 equals 3 times x minus 0. You with me? Okay? It's pretty common that you're asked for 3 levels of G. G at 1.5. G is just straight up the area accumulation function from -3 to 1.5 by definition. So that's going to require some geometric area calculations. Wouldn't you agree that that's the positive quarter circle, 9 pi over 4, plus a triangle, which is base times height divided by 2. What are the base and the height of the triangle? 1.5 and 3 divided by 2. You can read that. Okay? All right. What about G prime at 1.5? What is G prime's connection to F? G prime is equivalent to F at 1.5. F at 1.5 is just reading the F graph, which is 0. Last but not least, G double at 1.5. Connected to F. G double is equivalent to F at 1.5 F prime at 1.5, sorry, F prime at 1.5. What does that mean in terms of F? G prime is the blank of the graph. Slope. Okay, so G double is equivalent to F prime. F prime is the slope of F. What is the slope of F at 1.5? Well, it's probably the same as anywhere on this line. So what's the change in Y? Down 1, 2, 3, 4, 5, 6. Down 6. Over 3. So the slope is -2. G double at 1.5 then is -2. Okay? Last but not least, point of inflection. As in all steps, you make the big idea of calculus connection, then connect it to F. So G has an inflection point where G double, which equals what in F? F prime, which equals slope of F, changes sign. Inflection point in G double, and G is what? G double, which equals the slope of F, changes sign. Where is this at? Where does the slope of F change sign? So it's positive here, do you agree? Okay, and then it turns negative, so it's at x equals? Inflection point at x equals 0. It just said find the x value, so we don't have to find the y thing. Although, I guess we already had G at 0 somewhere. All right, that's the idea. This kind of question is the most common question on the AP exam. It is pretty much every year guaranteed. 95% of the time, it's a free response question of some sort. All right, we will practice this to death. This will be mine by the time you're done. Okay, that is that. Questions on last night's homework? How did it go? Not great? Or great? Did you mean to say great? How'd it go? Are you ready? You need to go to cotton or something? Okay. Okay. Did you hopefully graph it and set your window to 50 so you got something like this? Okay. Okay, it said label the left 0A and the right 0B. Mission accomplished? Okay, the left A was 9.8696. So I would take 869 or 870 or more decimals. B was 39.478. How about you? Do you agree? Do you agree? I hope so, because everything else is going to be wrong if you don't agree. Are we good? Okay, thanks, Tegan. That's one person. All right, using your graph in the signs of F prime, find the intervals. This is F prime's graph. Find the intervals where the original function was increasing and decreasing. So again, remember, I'm not asking where is this graph increasing or decreasing. That's ridiculous. You're based on the F prime graph, you're saying what was F doing. In this region, from 0 to A, wouldn't you say that F prime is positive because the F prime graph is above the axis? And if F prime is positive, then F is increasing. So it's F is increasing on 0 to A, and also B to infinity, not so much for 50 yet. Okay? And F is decreasing on A to B under the axis. Cool? All right. If F at 0 is 12, okay, whatever, and your work, given your work in C, should F at A be greater or less than F at 12? Well, here's the idea. I don't know what F's graph is, but I do know that because f prime is positive from 0 to a, f is increasing. Well, if f increased from 0 to a, then f at a should be greater than f at 12, yeah? Not f at 0, excuse me. Did you find f at a correctly? Did you get something like 18.2831? Okay, let me know if you need to see the work behind that. Fundamental theorem of calculus. Okay, so you would start by saying, how do I relate what I know, 0, to what I want, a? That's through a definite integral. From 0 to a, the area under f prime, by fundamental theorem, would be the antiderivative of f prime, which is f at the upper minus the lower. That's your first step. When I say fundamental theorem of calculus, there it is. That's it. Okay? Now you rearrange it to solve for that which you want. If you want f at a, if I want f at a, then I would move f at 0 or f initial over. In essence, then, f at a is the starting point plus the change. This represents the change. You're accumulating change. So that is where I got that by using your calculator to do the definite integral and adding the 12. Right? Should f at b be more or less than f at a? What do you think? Yeah, less. Because f prime is negative, f is decreasing from a to b. So you would say it's f at b is less than f at a, because f is decreasing on the interval from a to b. Okay? This is a little harder. This goes to, was your picture good? Should f at b be more or less than f at 0? Well, from 0 to b, I got increase and decrease. And how much increase and how much decrease is directly related to how much area. So the question really amounts to which area is greater. Well, if you do this well, you should have, I hope, I think the increase area was greater. Yeah? I don't know if I do this well. Did you get that the increase area 0 to a was bigger, or? I don't have this in my calculator. Oh, maybe I do have this in my calculator. Do you, right? 0 to a was bigger? Okay. If the 0 to a was bigger, then it increased more than it decreased. And so if it increased more than it decreased, then f at b is probably greater than f at 0, yeah? All right, so I would say f at b is greater than f at 0 because the increase area, which in math terms you would say the area from 0 to a, is greater than the decrease area. So the integral from 0 to a of f prime is greater than the area from, actually, the absolute value of the area. Obviously, it's greater if it's negative. B to a. Exactly. Yep. You got less than? Do I have this in my book? Let me see if I have this in my calculator. Oh, I mean. You have, oh, super. Yeah, I feel like the area below is a little more, yeah? It is a judgment call, but I think the area below is more. So, let's go back and redo this. I feel like less because the decrease area is greater than the increase area. On an AP test, it would be obvious. Okay. If you then find f at b would be the idea of going from, you could go from where you left off at A and then go to B, or you could just start all the way back at B, or 0, whatever you prefer. But you still have to set up a definite integral, fundamental theorem style. I'm actually okay if you went straight to the rearranged form. But I got it as an estimate, or my decimal answer, negative 0.056. value of 0.056. That actually verifies, yes, that is less than both f at A and f at 0, as we expected. Okay? Should f at 50 be more or less than f at B? F at 50 is, you didn't get that value? Maybe I didn't have my glasses in. Negative 0.56, what's the third decimal? Sorry. Okay. The conclusion still stands. Sorry about that. All right. What about f at 50? Will f at 50 be more or less than f at B? Well, it's increasing from B to 50, so f at 50 should be greater. I'll say everything. F at 50 is greater than f at B because f prime on B to 50 is positive, or f is increasing, something like this. Find f at 50. F at 50, I said, was f at 0 plus the change from 0 to 50. And I got as an approximation something like 3.4425. Agree? Okay, so what is the greatest possible value of f on the whole interval? Now, this is actually a big idea of calculus we'll talk about later, but the greatest possible value has to either be at an interior max, a relative max, or at an endpoint. Now, it's definitely, this isn't the absolute max because right away after 0 I started increasing, so it's definitely not that point. Up to A, it increased a ton. We said it decreased a little to B, but not as much as it increased. And then it increased a little from B to 50, but it never got anywhere close to where it was at A. And so the absolute max is f at A, which is the 18 number, 18.28. That's the greatest possible value of the function for k. Concave up. F is concave up if, talk to me about calculus ideas. F is concave up if f double is positive. Now, let's connect that to f prime. F double is the slope of f prime. So I need to basically find where is the slope of f prime positive. F double is positive if f prime is increasing or has positive slope. So, wouldn't I need to find that point because it's positive slope then, and that minimum because it's positive slope then? So I have two intervals where that's happening on 0 to 2.4674 and or 22.2066 to 50. Wait. Inflection points, big idea of calculus. F has inflection points if f double, which equals the slope of f prime, changes sign. Where does the slope of f prime change sign? Well, this is positive, then negative, so that's 1. And this is negative, then that's positive, so that's 1. So it's those 2 points, those extrema points again. This occurs at x equal 2.4674 and 22.206. Am I done? I got it. No, you need to find the y's that go with those. So how do you find f at 2.4674, which I hope you scored? Fundamental theorem, yeah. You could do the rearrangement stuff, but I think you'd see its starting point plus the change. That y value I got was 14. So one inflection point was 2.4674 to 14. The other was it 20-ish, 22-ish? And that's by fundamental theorem, 0 to 22-ish stored. I got 10 for that. So your 2 points are those 22.206. Boom. Good? All right. Backside. How'd the backside go? Not good? Let's see. All right. Find the value of f of negative 6. F of negative 6. How do I go from the derivative to f of negative 6? It's definitely not by integrating the equations. That's not the idea. You know f of negative 2 and you want f of negative 6. So write a definite integral connecting the two, yeah? So go from negative 6 to negative 2 of f prime. That's the antiderivative f at the upper minus the lower. So hopefully you found f of negative 6 by rearranging that. And I got 3.
Yes.
Okay? Do the same kind of work for f at the other one, 5. F at 5 is 10 minus 2 pi. Do you agree? No? How? Okay. So it would go something like this. In this case, the point I'm using is still negative 2, but now I'm going to 5, yeah? So by fundamental theorem, that would be f at 5 minus f at negative 2. Lower to the upper, right? So f at 5 is f at negative 2 plus the integral from negative 2 to 5 of f prime. F at negative 2 is given as 7, and now let's talk the area from negative 2 to 5. From negative 2 to 5, that's a half circle, but it's below the axis. So that's a negative area minus pi r squared over 2. Then a positive triangle, so plus base times height divided by 2. That's 7 minus pi times 2 squared over 2 plus 3 by 2 over 2. The plain old numbers come out to be 10, and the half circle's area is 2. That's where that's going. You follow? All right. B. At what intervals is f increasing? F is increasing where f prime is positive, which is on negative 6 to negative 2 and 2 to 5. Boom. Okay? For each of f at double at negative 5 and f double at 3, find the value or explain why it doesn't exist. First, connect f double to f prime. F double is what relationship to f prime? Slope of f prime. Okay? Slope of f prime, or the derivative of f prime, obviously, at negative 5. And at negative 5, the slope is down 2 over 4, so negative 1/2. You follow? What about f double at 3, which equals the slope of f prime at 3? Well, I want the tangent slope at 3. Is it this one? Or is it this one? Or is it, uh-oh. Yeah, it's uh-oh. The derivative does not exist at that point. That is dne because it is a sharp turn. Yeah. Okay? That's dne. E, find where f has a relative min. Start with the big idea of calculus. A function has a relative min where? Yeah, f prime goes negative to positive at. Now, do I actually look at the slope of this, or do I actually look at the graph? Yeah, the graph goes negative to positive. This is positive to negative. Remember, it's always left to right. So that's positive to negative. That's more like a max, right? The min is at 2. Okay? Find the x where f has relative max. We just said that. F prime is positive to negative at negative 2. Point of inflection. F has an inflection point where f double, which equals the f prime slope, changes sign. And that is at, the slope changes here, but does it change sign? It was negative before and it's negative after, so that's not it. How about here? Negative, then positive, so that's 1. How about this is positive, then positive, so not that. How about here? Positive, then negative, that is another. So inflection points at 0 and 3. The x and the y tuck on it. That sucks. All right. F at 0. Oh man, did we do f at 0? Have we found that yet? Oh shoot. So f at 0 by fundamental theorem. What'd you get there? I got 7 minus pi. Do you want to see where that comes from? F at 0 is 7 minus pi. Okay, so 0, 7 minus pi. Obviously, there has to be work to that, not just my answer. Fundamental theorem. And f at 3 is 8 minus 2 pi. Really? So there's your 2 inflection points. Okay? Find the interval where f is decreasing and concave up. So the first thing I do is gather all the conditions. F is decreasing if f prime is negative. And f is concave up where f double is positive or f prime slope is positive. So I need to find where f prime is negative but has positive slope.
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Negative with positive slope is down here and here. So 0 to 3.
The Dublin Spanish Honor Society presents a Thanksgiving canned food drive running from Monday, November 12th through Friday, November 16th. Donate non-perishable items such as oatmeal, peanut butter, and canned fruit to your third period class. The class with the most canned wins a party. Let's give back to the Jeffco community and help those who need this season.
Are you stressed? This Friday during Best Summer, we will have 3 different activities to help you de-stress. There will be office episodes of the Library Club, a NAPRA McKee 100, and a Just Dance Chess 100. Come and have some fun.
Speaker Sam Piquet will be here for 7 hours Fridays for FCA. He's a very talented youth speaker and you will not want to miss him. Join us for snacks and fun as we hear him speak in the library.
The International College Fair is offered at Dakota Ridge High School on Thursday, November 15th from 6:30 to 8:30 p.m. Over 11 countries will be represented. Best to pre-register. Stop by Counseling for additional information.
Is your last reminder to bring in your outerwear that you will no longer use and donate it to Last Club to Coast for Colorado Drive. Collection points are at each school entrance until tomorrow. Your donated items will be distributed to each Colorado resident to help them keep warm and healthy. Thank you for your generosity.
High school students, it's not too late. Pick up an audition packet for the musical Curtain in the choir room. Auditions will take place next Monday and Tuesday after school in the